Thank you so much for the invitation. It's my pleasure to talk to everyone about the DART mission. This is something that happened about a year ago, and I want to really talk about why we did it, what happened afterwards, and put it in a little bit of context to where we're going next. I was, or still am for another few days, the DART Observations Working Group lead. The mission is formally ending at the end of the month, and so we really have a lot of great information to share with everyone. So as I mentioned, impact was actually a year ago. So 1 year ago, we had the phenomenal first test of a planetary defense mission. All right. So what you're seeing here is an animation. You have the DART spacecraft that has released a CubeSat called LiChaCube. All right, and this is going to kind of show you the overall structure of the mission itself. So LiChaCube is released to fly behind the DART spacecraft. The DART spacecraft comes towards Dimorphos, which is a moon of Didymos, the larger asteroid off to the right. It impacts directly into that moon, creates a big cloud of ejected material called ejecta, and LiChaCube is there to watch that unfold. And that small CubeSat gives us a lot of the images, really the only images of what happened at the time of impact from close up in the system. All right, so why did we do this? Why did we even have a planetary defense mission? Why did we test our capability? Well, there's been a lot of attention recently when it comes to potentially hazardous asteroids and how they might come close to Earth. And one of the things that people don't really think about a lot is that we're actually constantly being impacted by extraterrestrial material. And so here is a map of the planet. And all of these circles here indicate a specific fireball. So something that came in through the atmosphere that was detected by sensors over the past few decades. And so you can see here, this is 1988 up until earlier this year. And all of these things, this is constantly happening. We constantly have material that comes here. The largest of these events happened in 2013, and perhaps people remember this being in the news. This happened in Chelyabinsk, Russia. And we had something of a size about 20 meters across enter the atmosphere. And this is predicted to happen approximately every few decades to centuries. But it was really particularly interesting because it called people's attention to planetary defense overall. And so one of the great things about this particular impact was that there were a lot of cameras pointed at the event itself. And so we could see the fireball come in, it brightens up the sky, the meteorite goes to land off in a field. And while it didn't create a lot of catastrophic damage like you might anticipate from a meteorite impact, it did have an actual effect on the humans around the area. And so this was largely through the shock wave that you could see here busting out windows, pushing down walls and things of that nature. And certainly, surprising a lot of folks. And so this, goes on and on. You could see a lot of different takes of this event. And so this is really something that pushed NASA in particular to really think about planetary defense. Now, what does that mean? Right, planetary defense means a lot of different things, actually. And this is all coordinated by an office called the Planetary Defense Coordination Office, as it turns out. And there's several different categories. And so you could see those here. And they range from finding near-Earth asteroids, and especially those that are potentially hazardous, understanding what materials those objects might be made of, and then understanding what you might do about it. And so essentially, again, we find them, right? We're doing these searches to find them. We want to understand them so that in the future, we might be able to build the tools to react to them. And so DART really falls under that mitigation category. And this is, again, the first full-scale test of a planetary defense mission. And you could see that there's a couple of other things that also fall under this category. And for something like Chelyabinsk, we wouldn't necessarily have built a DART spacecraft to go knock it off the course. We would really do something more localized. And so that's why you could see here that this also includes things like FEMA exercises. And so one of the things that I want to mention is that there are a lot of different near-Earth objects, right? They come in various sizes, they come in various compositions. And a lot of people really are thinking about the largest objects out there, such as this one up here. This is about 10 kilometers. And the impact frequency is really very rare. It says here about 1 per 100 to 200 million years. And so this is going to be the kind of object that we associate with the dinosaur extinction event, right? And so that was at the Chicxulub crater, which is here. And so the interesting thing about this from planetary defense perspective is that we are not concerned about it at all. There's a very small number of these objects, and we also know where they all are. And so we understand exactly where the orbit is relative to us, and we know that they're not a threat. But as you go farther to the left, you can see smaller and smaller objects, and those smaller and smaller objects are harder to discover. And so you can see that here by these pie charts showing the percentage that we have discovered in each of those populations. When it comes to something like Chelyabinsk, right, from the videos I just showed you, you actually can see that we haven't discovered a whole lot of objects in that size range. This is actually a relatively small thing, but it also doesn't really have large consequences should something like that come to the planet. It's certainly something that we need to be aware of, but it's not the kind of thing that we might need to send a spacecraft to mitigate. The sweet spot for that is going to fall in this size range here. All right. And so the reason that we're concerned with this size range in particular is it's large enough to actually cause some regional devastation, but it's small enough that we actually are not quite as efficient at discovering them. All right, so we've discovered about 42% of objects in this size range. And this kind of leads to some of the top priorities, especially the top priority when we designed the DART mission to begin with. And so the first priority, according to the National Academies, was for a space mission to test mitigation as a kinetic impactor. Right, and so kinetic impactor is essentially a spacecraft in this case that is going to go and crash into the asteroid in question. And so this specific spacecraft, DART in this case, is going to change the orbit of that potentially hazardous asteroid. And so really what we're thinking about is DART being this kinetic impact test at a realistic scale. These are finally the scales that we actually want to understand. These are the scales that concern us. And so here, if you look at this chart on the right, we have warning time. So essentially, how far in advance would we know that something might impact the Earth and how large it is? And so you could see that there's a lot of different options. If for something that's relatively small, then you're going to go with the civil defense option. That's something like knowing that the Chelyabinsk event would happen and telling people to stay away from windows or preparing for the damage that would come associated with that. And up here, as you get to slightly larger objects, which DART is targeting in this size range, you get into this kinetic area. And that's what we're talking about here. We're talking about taking a spacecraft and directly impacting into something else. There are no additional explosives. It is really just the momentum of the spacecraft going into the asteroid. All right, and so this really sets us up for why DART was interesting, and specifically why DART was a mission priority for the Planetary Defense Coordination Office. And so what was the mission itself? And so here's a summary slide that shows, again, what we saw in the video earlier. And so we have Dimorphos here in the center of the slide, going around the larger Didymos. And so you could see here the approximate sizes of both and the distance between them. This DART spacecraft is here. It is coming in for a head-on collision into this moon. It is followed by LICIACube, which is a CubeSat, so a very small satellite that was contributed by the Italian Space Agency. And the other key part here is the ground-based observations. And so we were using telescopes on the ground and some in space to understand what happened at the point of impact. And something that I'm going to come back to a little bit later is that in order to understand what happened, we had to understand the system before we hit it. And so there's a lot of different priorities here. So if we start with our goals here, the first goal is to target the binary asteroid system, to impact into Dimorphos, and then to measure specifically the period change. So how long it takes this specific moon to make one full revolution around the larger Didymos. And we're going to do that with the DART spacecraft. And in addition to being a full-scale planetary defense test, this was also a good place for us to test different technologies. And so there are a couple of really interesting things on the DART spacecraft, including a rollout solar array that you could see here. We used something called SmartNav, which was really, really important because SmartNav was the system that we used through the camera here, Draco, to navigate the last part of the mission. So in order to get DART to hit nearly as close to the center of the moon, Dimorphos, as possible. All right. And so as I mentioned, we're carrying along a CubeSat called LiChaCube. And so here you can kind of get a sense of the scale here from the units. And it has two different cameras on board with different capabilities. And essentially, we let LiChaCube go from the DART spacecraft 15 days before impact. And it trailed behind so that it could essentially watch the entire impact event and show the immediate aftermath. And so the closest flyby for this CubeSat was about 3 minutes after DART's kinetic impact at a distance of about 55 kilometers. And so I'll show some images from that flyby in a bit. And so one of the things that I really want people to understand about the DART mission is the scale. Because that's really important here. This is not an incredibly large spacecraft. This is actually something very moderately sized. And so here we have the rollout solar arrays before they were put onto the spacecraft itself. And you could see people here, right? So you could see kind of the people there for scale of the solar arrays. Here we have LiChaCube when it's arrived at the Applied Physics Laboratory, which is where everything was brought together prior to launch. And so you could see, someone essentially picking it up with a single hand. It's a relatively small spacecraft that we took along with us. Here is the pre-ship inspection. So this is before it left the Applied Physics Laboratory in Maryland to make the cross-country trip to Vandenberg Space Force Base in California. And so again, you can get a sense of the size of this complete spacecraft here. So here's the bulk of the spacecraft. Here are the rollout solar arrays. And here we have where LiChaCube is stowed on the side of the spacecraft. And then we put it on a truck and it drove all the way across the country. And normally I wouldn't actually mention this, but one of the things that I found interesting was the fastest way to Vandenberg was actually through Flagstaff. And so they passed through on the 40 at some unclear time. So it's not like we could have seen it go by, but it did in fact pass through our town on its way to Vandenberg. And so here is right before they closed it up on top of the rocket. And we launched in November of 2021. It was really a spectacular nighttime launch. It really lit up the sky. It was fantastic. And it was really exciting to be there. And one of the things that I thought was particularly interesting was that there were so many different groups of people there that had all contributed to the spacecraft itself. And so I have very specific memories of people cheering on different components of the mission. And somewhere nearby was actually the rollout solar array crew. And so they were particularly proud of their accomplishment, as many of the other groups were as well. And so to really bring back the size of the scale, here we have Didymos. Again, that's the larger one that our moon is going around, Dimorphos. So Dimorphos is around the size of one of the pyramids of Giza. And we have the DART spacecraft over here. And this size here is also accounting for those rollout solar arrays. But if you think about the main part of the spacecraft, it's really about the size of a very large vending machine. And so we have something the size of a vending machine impacting into the Great Pyramid of Giza and changing the way that it behaves in space. And so here is the outline of the mission again. And so remember, what we're doing is we're impacting the spacecraft into the moon called Dimorphos. And what was going to happen is the energy associated with that spacecraft is going to be transferred into the moon, and it's going to change the amount of time that that moon takes to go all the way around Didymos. And so before the impact, we knew that it took Dimorphos 11 hours and 55 minutes to make one full rotation around. And the question is, what is going to be the new orbit period? And this is going to tell us a lot about the momentum transfer. And one of the things to think about is that this isn't a game of billiards, right? We expect from our life experience that if you have something hit something else, it's going to behave in a relatively predictable manner. And if you take an introductory physics class, you're going to calculate what that predictable manner might be. But in this case, we have one additional component, and that is the ejected material, that ejecta that's going to come off of the surface of Dimorphos. And so we call this number beta, and it's the momentum transfer. And this is really what we're trying to test when we think about the DART mission overall. And so what we want to understand is how much does that ejecta coming off give an extra push to the moon to change the orbit period even more than if just the spacecraft hit it. And so here is a slide to kind of summarize our thinking here. And so beta equals 1 means no material comes off, no ejected material, a very small momentum increase. And so that's going to move the moon a relatively modest amount. Beta equals 2, we're going to have a moderate amount of ejecta coming off the surface, and that's going to move the moon a bit more because we have more momentum moving forward. And beta equals 4, well, that's going to be a lot of material coming off the surface and a really large momentum increase. Now, we know, because we are able to calculate it ahead of time, that if no material is ejected, the period change would be about 7 minutes. And it's negative 7 minutes, so that full orbit period would get shorter. All right. And so what we really want to do is see how much larger will this period change be compared to this 7 minutes that you might expect from just the pure kind of introductory physics class sort of change. All right. So how do we understand these orbits, and how do we really build off of here? Well, this all started when Didymos was discovered in Arizona with the Space Watch telescope, which is located outside of Tucson. And so these are the discovery frames from 1996. And you can see here, the blue oval is showing you this object moving across the field of stars. And I'm going to show several different animations kind of like this, because this is a lot of what we're doing. We're looking at the object through time. And so here is the discovery of the Didymos system, all right? And as time went on, we obtained even more observations. And so in this case, you could see Didymos moving across the field here. These are frames from 2021 at the Lowell Discovery Telescope out in Happy Jack. And these are so that we can build an understanding of the light curve of the system, which I'm going to get to in a second, because this is very important for understanding, again, how long the moon takes to make one full orbit. We also have used radar telescopes to understand the shape of the object itself. And so this was our best understanding of the shape of Didymos, the larger object, using radar data from 2003. And I'll show you some images later of what Didymos actually look like. And so we're starting to build our understanding, and this really goes back decades at this point. And I will note that in 2003, that's when we discovered Dimorphos. And we discovered it using a couple of different techniques. And this is the first one, and this is going to be really important to how we understand the system overall. And so if you're familiar with a lot of other kinds of astronomical science, then perhaps this might remind you of extrasolar planet transits and the way that people talk about them. And so on the bottom, we have kind of this moving line that's moving over this graph of brightness. And so for every high brightness, it moves across. That means you can see both of the objects. You can see Didymos and you can see Dimorphos, and there's no shadows. But as it moves around, there are going to be times in which Dimorphos goes behind Didymos, or it's going to come in front of Didymos and potentially cast a shadow. And so here you can see it go in front and then cast a shadow onto it. And every time this happens, every time you lose some amount of light, you get a dip in that light. And that dip can tell you something about time, right? So you build up a large collection of these light curves, then we can start to understand exactly how long it takes the moon Dimorphos to make one full orbit. And so it was actually, Dimorphos was discovered in 2003 using this technique at the same time that it was discovered using radar observations. And so it was a really interesting time. We got a lot of really great data. And then the Didymos system wasn't really observed for quite a while. But one of the interesting things to understand is that if you're going to hit an object and change it, you really need to understand the properties of that object before you change it. And so we needed to understand the orbit of Dimorphos, not just how long it takes, but also anything that we can understand about the orientation of that orbit. And so starting in 2015, we started observing fairly regularly, and it increased as time went on, this system, so that we can really define what that original orbit period was. And so that was a period of 7 years between when we started the observations and when we impacted into Dimorphos. And by the time we got to the DART impact itself, we knew the orbital period of Dimorphos to within 0.1 seconds. And so I find that to be really, really phenomenal that we were able to get the data so precisely and over such a long period of time that we had a really, really strong definition of how long that object took to make one full orbit. All right. And so that's all of our pre-observations, building up to understanding what the orbit period was. But as we were going into 2022, we had to make sure that we understood exactly what was going on, but also really prepare ourselves for the tasks ahead. And so here is one of our first images from last year of the Didymos Dimorphos system. We had a couple of observations in the week before as well. And so this was also taken with the Lowell Discovery Telescope out in Happy Jack. All right, so I've told you a lot about the groundwork, at least from an observational standpoint. And now I want to walk through the moment of impact, and then I'll talk a little bit about what happened afterwards. And so impact, like I said, was a year ago today. I hope many of you were able to watch the live stream or even be at one of the various different watch parties here in town. And so here is a set of images from the Draco camera on the DART spacecraft. And so this is the last 5.5 minutes. It's sped up, except for the last 6 images. The last 6 images will be shown in real time. And so you can see the Didymos as it goes by off to the left, and we're targeting in on Dimorphos. And the goal is to hit as close to the center of the moon as possible. And so you could see it coming into view. You could see that it's full of a lot of gravelly material. We have some boulders on the surface. It's going to be a very complex surface. And when I saw this at the time of impact, I thought, well, that's going to be a lot of ejected material, right? So we're all hoping for a really large period change. And so here is another video essentially showing the same thing, but I want to take a step back and talk about it again because we were using what was called SmartNav, which I alluded to earlier. And so essentially what's happening here is that we're taking images, both of Dimorphos, which you can see here at the top, and Didymos here at the bottom. And I will play this again so that people can see what's happening. And so we are using those images, and the software on board the spacecraft is using the images themselves to center the spacecraft. So it's done completely autonomously. We had no control over it at the time. And so, like I said, I'll go back here. And so you can kind of see a little bit of image jittering around, and some of that is due to those small adjustments that the spacecraft is making. And then at the very, very end, which you could see signified by the middle boxes going away, it is essentially decided that it is coasting in all the way to the end. And so on the left, you see the actual images that we were seeing and that I showed in the previous video. On the right, you could see it essentially as the camera is trying to center on it. So it's essentially just looking for where it is bright. It doesn't care what it looks like. It doesn't care that it has boulders on it. It just wants to know what's bright. And so that's why it's kind of got this washed out look here. And so I'll kind of pause here for a second to show you that. And so that's what you're seeing here. We're just seeing something that the spacecraft itself can guide itself into. All right. So here is the last full image of Dimorphos. All right, and so this is, again, that moon that we're about to impact into. So this is 11 seconds before the impact. You can, again, kind of get a sense of the kind of materials that are on the surface and very likely throughout the body. And so this is 2 seconds before impact. This is the last full frame that downloaded off of the spacecraft. And so the image is about 100 feet across. And again, you can get a sense of boulders, gravel material, smaller rocks, all sorts of stuff. And so to us as scientists watching this, that really indicated that there was going to be a lot of material thrown out into space. And one of the things that people have spent a lot of time thinking about in particular is exactly what happened. What was the physics of the impact? How did it crater? How did that material get thrown out? And one of the ways to understand that is to understand exactly where and what orientation that impact happened. And so there's been a lot of people working to recreate the surface based on all of those images and to recreate how the spacecraft would have had to impact into those surfaces. And so that's what you can see here at 2 different orientations, that the spacecraft essentially went down into this area sort of between those 2 boulders, and you could see those rollout solar arrays going out to the side. All right, so, all right. All right, so I have a visitor in my room. All right, so we have here an image from that CubeSat from LICIACube, which again was contributed by the Italian Space Agency. And this was about 3 minutes after DART's impact. Okay, and so you can see the distance here from LICIACube to Dimorphos. This bright kind of washed out thing is Didymos. All right, so that is Didymos right there. And up at the top, we have Dimorphos. And specifically, you can't really see Dimorphos itself because you see all of this ejected material coming off. And you can see all of these streamers here in particular. And so there's a couple people who did some image processing to really be able to look at the structure of those. And so the contrast in this box is kind of the original contrast. And then they increased it. They doubled the contrast with each of these successive boxes so that you could see the streamers here coming out. And so this gives us a sense that the impact event and all of this material coming out was actually incredibly complex, which is really, really interesting because we've never been able to run an experiment like this in a laboratory, right? This is going into a very loosely consolidated gravel pile in 0G. And so what's going to happen? Well, you're actually going to get something that's really profoundly interesting. Although I probably would have said it's really profoundly interesting no matter what happened, but it's been really, really special. And so here is a set of images from the LICIACube spacecraft. As it is approaching, you could see that spray of ejected material, and then you could see that LICIACube has passed the Didymos-Dimorphos system, and you could see that spray of material receding out behind it. And using all of these images and those images from before, we're able to recreate models of what that impact event must have been like. And so here is our best understanding of the shape of Dimorphos itself. And here you could see the ejected material spraying out, and you could see kind of those streamers that I indicated in the actual images. And so people have been spending a lot of time thinking very carefully about how to recreate this so that we can understand what happened and hopefully be able to make some real scientific advances for the fields of impact cratering and ejecta. All right, so the really interesting thing about a planetary defense mission in general, but also this one, is that this really got the interest of the entire planet. And so this map here shows all of the telescopes in our worldwide observing campaign. All right, and so you could see that we had telescopes on all 7 continents. We had really, really large telescopes, some of the largest ones in the world, and we had some relatively small telescopes. We had universities contributing. You could see Michigan State up here, and you could see really just the sheer amount of observers that were involved in this effort. And over here on the bottom left, you can also see that we had 3 different observatories in space. We had Hubble, HST. We had the newest space telescope from NASA, JWST. And the Lucy mission, which is a mission to the Trojan asteroids that was making a close approach to Earth for a gravity assist around the same time. So we got very lucky with the timing of that mission in particular. And all of these folks were able to contribute a large amount of data. And so here is just a kind of a smattering from different institutions. And you can see from all of these different continents, the different kinds of observations that we had. A lot of folks were really able to share what the evolution of that ejected material looked like afterwards. And that's something that I have a lot of pictures of, because it's been really a fantastic time. And so this is Didymos right before and through impact. And so you could see the stars moving very rapidly in the background, because Didymos is actually really close to Earth, which makes that movement very rapid. And you can see a very, very large, and so that means a bright object, shed off this very rapidly ejected material and remain incredibly bright. Right. And so as we loop back and forth, we could see again the moment of impact followed by the brightening of the object, the shedding of this extra material, and it continues to move across the sky. And so we were really excited to see this, because this was our first visual confirmation that something extraordinary was happening, right? We didn't see the Leacha Cube images right away. All we knew was that the spacecraft no longer existed. And we had hoped to see something really phenomenal such as this. All right. All right. So I'm going to go back, and one of the things that I want to remind folks as I go back to the light curve video is that this is a lot of material, right? We have this asteroid. It gets really large. It gets really bright. And part of that is because we threw a lot of material up into the system, and that material is going to stay there for a little bit. And so now we're essentially back to thinking about the light curves. And what we want to do is actually pretty complex, because we're following these light curves as it goes around. And my moon appears frozen, but my timer is still going across. But now we also have a whole lot of material that's been ejected into the system, right? And so we have this nice view where we have the moon going around the larger object, but there's also just stuff everywhere now. And so it was very complicated. And at the time, we weren't entirely certain how long it would take for us to be able to see these mutual events. That's what all of these dips are called. We didn't know how long it would take to see those events again. And therefore, how long it would take us to understand how that orbital period had changed. And so the first detection of any change to the orbital period came using radar. And so this was using the Jet Propulsion Laboratory's Goldstone radar out in California with the Green Bank Observatory in West Virginia. That's how we were able to get these images. And so we first detected a period change about 12 hours after impact. Now, let me walk you through these so you can understand what we're actually seeing here. So this is from 2 different days. And here you're essentially seeing the side, kind of what we call the limb of Didymos. So again, that's the larger of the 2 objects. And here in these little green circles, this is Dimorphos. All right. So we can see we have, that limb of Didymos. We could see where the moon actually is, and we can use our understanding of orbits to draw that orbit. We know where Dimorphos would have been if we hadn't hit it. And that's these blue circles here. And we can see that it's no longer in those locations. And so we could start to use the relative changes and also follow it over time to reconstruct that time period that it takes to make a full orbit. And so here is a set of images. Again, we have kind of this limb of Didymos here, and all of these circles are showing where Dimorphos is, and we're able to reconstruct that orbit. And so using these detections, which again started about 12 hours after the impact, we were able to start to narrow down how much the period had actually changed. All right. So if we go over to the light curves, it was an incredibly complex process. And so this is very similar to the animation I showed you earlier, where we have the moon moving around the larger object. But in this case, this is actually showing the true orientation of the two objects with respect to us on the ground with our telescopes. And so one of the things I want to point out is that Dimorphos is not actually going in front of Didymos at this time period, but it is casting really the smallest of shadows when it passes in front. And so you can kind of see it as it comes around here. It's casting a relatively small shadow along the bottom. There it goes. And then it is going to go into shadow when it goes along the other side. And so not only do we have a complicated geometry of the system, but we also have clouds and clouds of material. And so over here on the left, I have an image from around the same time period as the first time we were able to see the signal of the moon again in the light curve. And so you could see here that there is a lot of material that has been ejected. It's not just a single point of light, it's a big fuzzy point of light. And so again, so we had radar at 12 hours, at 29 hours after impact, that's when we're able to see the moon through the light curves. And so now we can really start to build up our picture of what happened. And so this is a slide from one of the NASA press conferences. And in fact, this was from the press conference where they announced the period change for the very first time, which was a couple of weeks after impact. And so on the top, we have kind of a way that we're representing the light curve. So this is how bright Didymos is, and the days are going all the way across. And you can see where we have data from all of these little blue dots here. And we have two nights that are zoomed in on the bottom here. And so if we look at September 29th, we could see a gray arrow. And that means that we would expect a dip in light right here where this gray arrow is pointing if we hadn't changed the orbit at all. But instead, we saw the dip in light over here. All right, and so that indicates a new orbital period of 11 hours and 22 minutes. If you go over here to October 4th, we're showing something very similar. It's a different light curve, it's a different day, but again, we have marked where we would see that dip in light if the period was unchanged. And then over here on the far right, we could see that we're actually seeing it enter into this dip of light before the data ends. And so again, that is something that agrees with this new orbital period of 11 hours and 22 minutes. All right, so if we go back to our initial diagram of what we were observing, we could see here, right, we have the original orbit period of 11 hours and 55 minutes. And after we take not just the data that I showed you, but the data that we took for months afterwards, we didn't actually stop observing light curves until March of this year. And so we observed for about 6 months after impact. We actually found that the orbit period changed by about 33 minutes. It was 33 minutes shorter. And the accuracy on that is plus or minus 1 second. So it's really phenomenal accuracy. And so the new orbit period, right, the time it takes Dimorphos to make one full orbit is now about 11 hours and 22 minutes. I was repeating myself. And so that is what we have going forward. This is our understanding of the system. And the thing that we know is that an orbit period change of 33 minutes is definitely bigger than 7 minutes, which is what I said the orbit period would change if there was none of this ejected material. So we know that the momentum enhancement isn't 1, it's bigger than 1, right? And so I will get to how much bigger than 1 in a second, but I also want to put a little bit of this back into scale, right? And so here is Dimorphos. Here's another building that we can compare it to. Right before I compared it to the Great Pyramid of Giza, this is the assembly building where a lot of spacecraft, especially the space shuttle in particular, were housed when they were at Kennedy Space Center. And so we have a very, very large building. And Now we're looking at an object that has a lot of material that was thrown into space. Well, we don't have a complete understanding of exactly how long that tail was, but we know it was at least as long as this blue arc that is going around the planet Earth here, right? So this is a substantial amount of material that is eventually trailing behind this asteroid. And the amount of material that has come off of this due to this impact was probably at least 6 rail cars. And I like this slide in particular because we see rail cars here in Flagstaff all the time, right? So you have a sense of how large each of these cars is. And we're still working on narrowing it down. So it's at least 6, but it could be as many as 60 cars full of material that was blown off at the moment of impact. All right. And so here's another representation of this momentum enhancement factor, right? You have DART impacting into these 3 different dimorphos objects. On the left, we have no ejecta. It has some period change. In the middle, we have some amount of ejected material. It has a more larger push. And then on the far right, we have a lot more material coming off the surface. And each of those is going to have a different orbit period change, right? So I'm going to let the first part of this play out again. So you could see how more ejecta means a larger push. And it's literally from that material pushing off the surface as it is ejected. And so we actually ended up having this number be 3.6. So this momentum enhancement factor is 3.6. And that's not something that's really intuitive for a lot of people, and that's okay. The reason that I want to show this slide and give you the number in part is to show that this is really what we were building the entire mission around. Now we understand how ejecta can really influence these period changes. And so if we actually did need to mitigate the threat from an asteroid, we can start to use this data point to extrapolate what our choices would be. And so that's why this test was particularly useful. And so I'm going to finish up here by going through a handful of slides that show what happened, not just in the days and hours after impact or weeks, but really show what happened to the ejected material over a long time frame. And so here is an animation of images taken with the Hubble Space Telescope. And so this starts from right before impact and goes to 18.5 days after impact. And one of the things about Hubble is that the pointing wasn't very accurate because Didymos was so close to the planet. So that's why you might see some of the images be cut off. And so as we see it, we see a bright object, we see a lot of material get thrown up, we see it spread out behind the asteroid in particular, creating a tail. And here is a panel of all of those tail images. Again, this is from Hubble Space Telescope, and so it goes in alphabetical order here from not long after impact until about 18.5 days after impact. And so you could see it get very bright. You could see a lot of ejected material all around. And eventually, as time goes on, a lot of this material starts to flow behind the object. And so this is in the direction opposite of the sun. And so this is very comet-like behavior from this material. And so it really looked like a comet to our telescopes. And one of the interesting things that I do want to point out is that at some point, for a very brief period, it actually had 2 tails. And so you could see a tail here and a tail here, which probably means that we had something else hit the surface several days after the initial impact. And so what could that possibly be? Well, it's very likely that it was a boulder, right? We saw all those boulders on the surface right before impact. Those were also thrown up with all of the other material. And Hubble observations showed that at the end of 2022, so a few months after the impact itself, there was a field full of boulders all around the object. And so here you could see they're all circled and laid out here. And the largest boulder is about 7 meters across. And so relatively moderate size, but these are large objects. And so it's very likely that one of those could have fallen back onto the surface of Didymos. And so, I want to wrap up here with a set of images essentially showing this tail through time. And so that the tail grew quite long. And so you can see here this animation again from the Little Discovery Telescope. This is 52 days after the impact. We have Didymos moving up against the field of stars, and you can see that we have a really large tail, and it's really quite phenomenal. And the interesting part about this is that the tail persists. It's still there. Here is another image from the Little Discovery Telescope in March. And so this is 168 days after the impact. And again, there is still a tail here. And we've been following it for as long as we possibly can. This is a stack of images, so a whole bunch of images added together from the Hubble Space Telescope, pushing 300 days after impact. And so this set ended in early July, and you could see here Didymos and Dimorphos together, followed by this long tail of material again. And so it's really impressive that the tail persisted for over 9 months. And it is really a shame that, we observed for such a long time, but, at some point those observations had to end. And they had to end because Didymos is now too close to the sun in the sky for us to be observing. And so we're looking forward to some time early next year in 2024 when it'll be visible again. And we can look to see, is the tail still there? What's going on with the orbital period? Any other questions that we have open, we could start to revisit next year. And so I do want to kind of wrap up this DART segment in talking about this mission. This was really tremendously successful. And one of the things that's particularly interesting is that this was the first time that humans have moved a celestial object, right? We're actually able to design this experiment. We're able to use this autonomous guiding to find the center of the moon, impact there, and have a really tremendous amount of information about the object itself, but also about the changes that we made to the object, right? And so we actually had a very large orbit period change, and that shows that ejected material really had a large contribution to that orbit period change, which is really a phenomenal result. It's exactly what we had been hoping for. And because we had so much material come off and so much of an extra kick from that material, that means a lot for how we would use this technique if we had to in the future. And so if you wanted to use a kinetic impactor to deflect an asteroid, then maybe you can use it on a larger asteroid than you might have anticipated before, in order to make that deflection and to essentially save the planet, right? And so this is one of these things where we can now take what we've learned and apply it across to various other topics. All right, and so I'm going to wrap up here by saying that we are not quite done yet, not with the Didymos Dimorphos system. We are now in the process of handing over leadership of this planetary defense initiative to the European Space Agency's Hera mission. And so they are in the process of building their spacecraft. They are on track for launch in the fall of next year. And they're going to rendezvous. They're going to go spend time, quality time in the Didymos Dimorphos system. They're going to study the two objects starting in early 2027. And so here is kind of an overview slide showing the different parts of our joint investigation. On the left, you could see DART impacting into Dimorphos. You could see the ground-based telescopes teaching us about all of the different things that happened after the impact. And like I said, we're essentially transferring over the leadership of this to the Hera folks. And so they're launching again late next year. They're taking along a couple of CubeSats as well. And they're going to spend a lot of time in the system studying everything in detail, looking for the impact crater that we caused, trying to understand the composition very, very specifically. And so it's going to be a really exciting time as we use the data that they're going to send back to fill out some of the questions that we still have about this system, and really, hopefully, help us as we start to make bigger plans for planetary defense overall. And so that's it. I'm happy to take any questions, and thank you so much for letting me speak with you.
Excellent. Thank you, Dr. Thomas. That was really mind-blowing and interesting. You see it in the news, but you don't really think about the complexities of how this plays out. So it looks like we have a question in the chat. One of the individuals asked what the altitude of Dimorphos's orbit was.
The altitude of Dimorphos's orbit, like the way that it's inclined. I don't know that number off the top of my head, but it is something that we do know.
And they also ask, how would the strategy and hardware of a mission to deflect an asteroid differ between a solid asteroid at a beta equals 0 and an asteroid with a high beta value?
Right. So one of the interesting things about the planetary defense portfolio overall is that we need to start to think about some of these questions, right? And so the next planetary defense mission is a discovery mission, so we could find more objects. But the third mission that people are starting to talk about is what's called a rapid reconnaissance flyby. And so this would be a fairly simple spacecraft. You would launch it in the direction of the object that you're worried about, and you would be able to get some information. And amongst that information that people would be looking for is it what we call a rubble pile? Is it basically just, gravel that's sort of held together by gravity? Or is it a solid boulder? And so then we can actually make the appropriate plans for how you would mitigate it. And so it would have to be very fast. It would have to happen quickly so that you can use the rest of the time for the actual mitigation, right? The kinetic impactor and things like that. And so people are right now thinking about how to make that mission and what that would tell us about a specific object.
Excellent. They also clarified altitude. They're thinking the distance from Didymos.
The distance from Didymos. So that makes a lot of sense. I can put this back up. And so here is the separation between the two. And so it's a little over a kilometer.
What was the new orbital period? Was that the 11 hours and 22 minutes?
Yes.
And we have another question. Was there any consideration of retracting the solar array right before impact to potentially increase the impact effect?
No, there wasn't. I don't know that they could retract. I think they were a one-way trip for the solar arrays as they were designed for this mission. But there was certainly a lot of thought put into the impact modeling side to think about, how much does the solar array actually contribute to the entire thing, right? We think that the core spacecraft is going to be a large part of that impact event, but what actually happens to the solar arrays? And so there are some people that speculate that parts of the solar arrays might still exist on the surface. I don't know. I'd be curious to see.
That's really interesting and really exciting to sort of think about how sharing science in this way. You highlighted all of the telescopes that were sort of watching this. Is that something that's really common, you think, in the context of this type of research, or was this specific to DART, that it was just such an important and exciting mission?
Well, I mean, I think that it's all of those things, right? Planetary defense is very international, right? We're talking about the entire planet. This is a worldwide concern. And so we have a lot of international participation because this is something that people are interested in studying. And, we also were in a very interesting place when this impact happened. Didymos and Dimorphos were making a relatively close flyby to planet Earth, which meant that it was relatively bright. In fact, it hadn't been this bright since 2003, and it's not going to be this bright until sometime in the 2060s. And so it was a really good moment to do this. And that meant that we could use all sorts of telescopes. We didn't have to rely on only the biggest ones. And by really opening that up, we were able to get so much more participation. And I think that's one of the reasons that we had people just all over the world, because they could actually contribute meaningfully to this project.
That's really awesome. Are there any upcoming projects like DART planned?
I think right now, DART is very unique. I think there's a lot of folks that are going to transition and work on Hera, or kind of work on the peripheries of Hera. But it's a very different mission, right? And will be done in a very different way. And so right now, this is the only mitigation test mission, and I will have to see what comes up next on the planetary defense future plans.
Will you be working on future projects like that?
I certainly hope so, but it's all up to if it was up to me, absolutely. But it's all up to much larger powers like NASA and the European Space Agency.
Well, excellent. I'm going to ask one final question. If anybody else has any that they want to add in the Q&A or the chat, let me know. But I was just wondering, for any of our younger viewers in the audience tonight, what are some of the educational pursuits they might want to consider if they ever want to do, a really awesome kind of job like this, beyond, you mentioned introductory to physics classes.
Right.
What would you encourage them to do if they're in middle school, high school, or even in college right now?
Well, I mean, I think it depends, right? I focused completely on the science from especially from a telescope perspective, but there's a whole side here that really didn't get highlighted at all, and that's the engineering side as well. And so I think that there's a lot of different ways to be interested in projects like this. And so I think it's up to folks to think about what part of these questions do they find interesting. Do they want to build spacecraft? Do they want to use telescopes? Do they want to run models of what the ejected material is doing, right? These are all different skill sets, and they all have different entry points, but really start to think about what actually interests you, and then look into what you need to get there. What kind of classes do you need to take? Do you need to get an internship? Do you need to get a mentor to help you through it? Because all of these things are going to be a little bit different. And certainly just really understand that it takes time. It takes time to build these projects. This is probably the fastest NASA mission to ever happen, from selection to build to impact to being done, right? A lot of these other NASA missions take decades. And so there's a lot of patience built into how we do all of the solar system science.
Well, perfect timing. That was absolutely fantastic. I learned a ton. This is not necessarily my forte, so this is really informational. And I appreciate all those kind of key pointers about engineering too, that students can come at it from so many different scientific perspectives. And we really appreciate you. I wanted to thank you for being here. Thank everybody for attending. Please check us out on scifest.org, complete our survey, and Dr. Thomas, good luck in your future endeavors.
Thank you.